Imagine a world where the ground beneath your feet is an ocean of molten lava, where diamonds rain from the sky like hailstones, and where winds rage at speeds that would tear apart the strongest spacecraft we've ever built. Now imagine a planet so dark it absorbs 99% of the light that touches it, a wandering world cast adrift in the cosmic ocean, or a planet with a surface so hot it can melt titanium. These aren't the creations of a sci-fi writer's fevered imagination. They're real places, actual planets that exist in our universe, waiting to be explored. Welcome to the scariest planets in the cosmos, a journey that will challenge everything you thought you knew about the universe we live in. In the next 90 minutes, we're going to take you on a tour of 8 of the most terrifying, awe-inspiring, and downright weird planets ever discovered. These are worlds that push the boundaries of physics, planets that make the most inhospitable places on Earth look like paradise in comparison. But why should you care about planets you'll never visit, orbiting stars you'll never see? Because each of these cosmic nightmares holds a key to understanding our own world and our place in the universe. They're natural laboratories, testing the limits of what's possible in planetary science. By studying these extreme worlds, we gain insights into the delicate balance that makes Earth habitable and the potential fates that could await our own planet. So fasten your seatbelts, space explorers. We're about to journey to the most terrifying corners of the cosmos. And trust us, after this voyage, you'll never look at the night sky the same way again. Before we dive into the depths of space, don't forget to hit that like button and subscribe to our channel. Because once you've seen what's out there, you'll be craving more cosmic horror. Now, let the interstellar nightmares begin. The Infernal Furnace. Kelt 9b. As we venture into the depths of space, our first stop takes us to a world that redefines our understanding of heat and hellish conditions. Welcome to Kelt 9b, a planet so extreme it pushes the boundaries of what we thought was possible in the cosmos. Kelt 9b orbits a star called Kelt 9, located approximately 670 light-years away from Earth in the constellation Cygnus. But this is no ordinary planet-star pair. Kelt 9 is a blue A-type star, nearly twice as hot and 2.5 times more massive than our Sun. And Kelt 9b, it's a gas giant that makes Jupiter look like a cosmic lightweight. But size isn't what makes Kelt 9b truly terrifying. It's the heat. This planet is so close to its star that it completes an orbit in just 1.5 Earth days. The result? A world that's hotter than most stars in the universe. Let that sink in for a moment. We're talking about a planet with a dayside temperature of around 4,300 degrees Celsius, or 7,800 degrees Fahrenheit. That's hotter than 80% of all known stars and even some red dwarfs. It's a temperature so extreme that it challenges our very definition of what constitutes a planet. At these temperatures, the word surface loses all meaning. There's no solid ground on Kelt 9b, no oceans, not even a clear boundary between the planet and space. Instead, the entire planet exists in a state of matter beyond what we typically encounter. Its atmosphere isn't just hot, it's a seething cauldron of dissociated molecules and vaporized metals. On Earth, we're used to thinking of metals as solid, stable materials. On Kelt 9b, metals like iron and titanium exist as gases, swirling in the planet's bloated atmosphere. The heat is so intense that it breaks apart hydrogen molecules, the most abundant element in gas giants. This dissociation of hydrogen molecules is a process typically only seen in the atmospheres of stars. But the torture doesn't end there for Kelt 9b. The planet is tidally locked to its star, meaning one side always faces the scorching heat of Kelt 9. This creates an extreme temperature gradient between the day and night sides of the planet. While the day side bakes at temperatures hot enough to vaporize metals, the night side, though still incredibly hot by Earth standards, is cool enough for some of these materials to recondense. This temperature difference drives ferocious winds that circulate around the planet, carrying vaporized metals from the day side to the night side. As these metals cool and condense, they likely form exotic clouds of liquid metal droplets. Imagine that for a moment, a planet where it rains molten iron and titanium. The sheer intensity of the star's radiation is also causing Kelt 9b to lose mass at an alarming rate. The planet's atmosphere is literally boiling away into space, with estimates suggesting it could be losing up to 10 billion kilograms of mass every second. This raises profound questions about the planet's long-term fate. Will it eventually be whittled down to its core, leaving behind a barren, rocky world? Or will it be completely devoured by its star before that can happen? Kelt 9b's extreme conditions make it a natural laboratory for testing our understanding of planetary physics. Its discovery has, well, forced astronomers to reconsider what conditions are possible on exoplanets, and has expanded our understanding of how planets form and evolve, especially in close proximity to hot, massive stars. The planet was discovered in 2017 using the transit method, where astronomers detect the tiny dip in a star's brightness as a planet passes in front of it. But Kelt 9b's discovery was just the beginning. Subsequent observations using various telescopes and techniques have revealed more about this hellish world. Spectroscopic observations have confirmed the presence of vaporized metals in Kelt 9b's atmosphere. These observations have detected the signatures of iron, titanium, and even rare earth metals like scandium and yttrium in gaseous form. Each of these detections tells us something about the extreme conditions on the planet and provides clues about its composition and history. The planet's extreme heat also makes it an excellent target for studying atmospheric escape. By observing the planet in different wavelengths of light, astronomers can track how its bloated atmosphere is being stripped away by its star's intense radiation. This not only helps us understand Kelt 9b's fate, but also provides insights into how atmospheric loss might have affected other planets, including those in our own solar system. Kelt 9b's discovery and subsequent study have also sparked discussions about the potential for life in the universe. While Kelt 9b itself is far too hot to support any form of life as we know it, its existence raises questions about the diversity of planetary environments out there. If a planet like Kelt 9b can exist, what other extreme worlds might we find? And how does the existence of such planets influence our understanding of habitable zones and the potential for life elsewhere in the cosmos? The study of Kelt 9b also has implications for our understanding of planetary formation and migration. Traditional models of planet formation struggle to explain how a gas giant could form so close to its parent star. The intense heat and radiation would typically prevent the accumulation of enough material to form a planet. This suggests that Kelt 9b likely formed further out in its solar system and migrated inward over time. But how did it get so close to its star without being torn apart? And how long can it survive in its current orbit? These questions are at the forefront of current research, driving new models of planet-star interactions and planetary evolution. As we continue to observe and study Kelt 9b, we're likely to uncover even more surprises. Future missions like the James Webb Space Telescope promise to reveal even more details about this extreme world. We might be able to create more detailed maps of its temperature variations, study the dynamics of its atmosphere in greater detail, and perhaps even detect signs of its ongoing destruction as it slowly evaporates under its star's relentless assault. Kelt 9b stands as a testament to the incredible diversity of worlds that exist in our galaxy. It reminds us that the universe is often stranger and more extreme than we can imagine. As we move forward in our exploration of exoplanets, worlds like Kelt 9b will continue to challenge our understanding and push the boundaries of planetary science. In many ways, Kelt 9b is a planet of superlatives. It's among the hottest, most extreme, and most inhospitable worlds we've ever discovered. But in its hellish conditions, we find a cosmic laboratory, a place where the laws of physics are pushed to their limits. By studying this infernal furnace, we gain insights not just into the nature of hot Jupiters and extreme exoplanets, but into the fundamental processes that shape worlds throughout the universe. As we leave Kelt 9b behind and prepare to explore our next cosmic nightmare, we carry with us a new appreciation for the sheer diversity and extremity of planets in our galaxy. In the forge of this infernal furnace, our understanding of the cosmos is reshaped, reminding us that in the study of these alien worlds, we ultimately learn more about our own place in the universe. The Diamond Downpour. From the scorching inferno of Kelt 9b, we now journey to a world that glitters with an unearthly brilliance. Welcome to 55 Cancri E, a planet that challenges our understanding of planetary composition and formation, and sparks our imagination with the possibility of diamond rain. Located approximately 41 light-years away in the constellation Cancer, 55 Cancri E orbits a sun-like star in a binary system, but don't let its proximity to a familiar star type fool you. This world is anything but ordinary. 55 Cancri A belongs to a class of planets called super-Earths, a type of planet not found in our solar system. These planets are more massive than Earth, but less massive than ice giants like Neptune and Uranus. What sets 55 Cancri E apart, even among super-Earths, is its potential composition. Based on measurements of the planet's mass and radius, scientists have proposed a startling possibility. This world could be composed largely of carbon, much of it in the form of diamond. Let that sink in for a moment. We're talking about a planet where diamond isn't just a rare, precious stone, but a fundamental building block of the world itself. If the diamond hypothesis is correct, up to a third of 55 Cancri E's mass, the equivalent of about 3 Earth masses, could be diamond. But how could such a world come to be? The story of 55 Cancri E's formation is intrinsically tied to the composition of its parent star. The star 55 Cancri A has an unusually high carbon-to-oxygen ratio compared to our Sun. This overabundance of carbon in the protoplanetary disk from which 55 Cancri E formed could have led to the creation of a carbon-rich planet. Under the extreme pressures found in the interior of 55 Cancri E, much of this carbon would be compressed into crystalline form, in other words, diamond. The planet's interior might consist of a layer of diamond overlying a core of iron. Above this, there could be a layer of graphite, and on the surface, a thin layer of carbon-rich minerals. However, the surface of 55 Cancri E is far from a serene field of glittering gems. This world orbits extremely close to its star, completing an orbit in just 18 hours. As a result, its surface temperature is estimated to be around 2,400 degrees Celsius, or 4,352 degrees Fahrenheit. At these temperatures, the surface is likely to be a seething ocean of lava. The extreme heat and pressure on 55 Cancri E create conditions unlike anything we've encountered before. In the planet's atmosphere, silicon-based minerals could be vaporized by the intense heat, forming a thick, choking haze. As this mineral vapor rises and cools, it could condense into droplets, creating rain unlike any we've seen before, a rain of molten rock and potentially diamonds. Imagine standing on the surface of 55 Cancri E if such a thing were possible. Beneath your feet would be an ocean of molten rock, potentially laced with diamond dust. Above, the sky would be a roiling mass of superheated gases and vaporized rock. And occasionally, a glittering rain would fall, not of water but of liquid rock and perhaps even microscopic diamonds. The study of 55 Cancri E has been a journey of discovery and revision. When first discovered in 2004, it was thought to be a Neptune-like gas giant. As our observations improved, we realized it was much smaller and denser, a super-Earth. The diamond hypothesis was first proposed in 2012, based on models of the planet's interior that best fit the observed data. However, science is a process of constant refinement, and subsequent studies have both supported and challenged the diamond planet hypothesis. Some models suggest that 55 Cancri E could instead be a water world with a steam atmosphere. Others propose that it might have a more traditional rocky composition, similar to Earth but with a much hotter surface. This ongoing debate highlights an important aspect of exoplanet science. Much of what we know about these distant worlds is based on models and indirect observations. We can measure a planet's mass, radius, and orbit with reasonable accuracy. We can even detect some components of their atmospheres. But determining the exact composition of a planet millions of kilometers away is a challenging task, requiring us to combine the data we have with our understanding of planetary formation and physics. Regardless of its exact composition, 55 Cancri E remains an object of fascination for astronomers. Its proximity to Earth in cosmic terms and its position around a bright, easily observable star make it an excellent target for study. Observations from space telescopes like Spitzer and MOST have revealed intriguing details about this world. One of the most puzzling aspects of 55 Cancri E is its apparent temperature variations. Observations suggest that the planet's hot side is much hotter than we'd expect, even given its close orbit. Moreover, the temperature seems to vary significantly over time, suggesting some form of dynamic process at work. These observations have led to some intriguing hypotheses. Some scientists suggest that 55 Cancri E might have a substantial atmosphere despite its high temperature. This atmosphere could be helping to distribute heat around the planet. Others propose that the planet might have active volcanoes, whose eruptions cause the observed temperature variations. Another fascinating possibility is that 55 Cancri A is not tidally locked to its star, as we might expect for a planet in such a close orbit. Instead, it might be in a 3-to-2 orbital resonance, similar to Mercury in our solar system. This would mean that the planet completes 3 rotations for every 2 orbits, leading to a complex pattern of heating and cooling that could explain the observed temperature variations. The potential for active volcanism on 55 Cancri E is particularly intriguing. On Earth, volcanic activity plays a crucial role in regulating our planet's temperature and contributing to the carbon cycle. On 55 Cancri E, volcanism could be occurring on a much grander scale. Massive eruptions could be constantly reshaping the planet's surface, spewing carbon-rich material into the atmosphere, and perhaps even contributing to the hypothesized diamond rain. The study of 55 Cancri E also has implications for our understanding of planetary systems as a whole. This planet is part of a system containing at least 5 planets, orbiting a binary star. The fact that such a system exists and appears to be stable challenges our models of planetary formation and evolution. How did these planets form and migrate to their current orbits? How do they interact with each other and with the binary star system? These are questions that continue to occupy planetary scientists and astronomers. Moreover, 55 Cancri E and planets like it are helping us to expand our understanding of what constitutes a potentially habitable world. While 55 Cancri E itself is far too hot to support life as we know it, studying extreme worlds like this helps us to understand the boundaries of planetary habitability. Could life exist on a carbon-rich world under different conditions? What would such life look like? These questions push us to expand our definitions and think creatively about the potential for life in the universe. As we continue to study 55 Cancri E, new technologies promise to reveal even more about this enigmatic world. The James Webb Space Telescope, with its unprecedented sensitivity and resolution, may be able to provide more detailed information about the planet's atmosphere and surface conditions. Future missions might even be able to directly image the planet, providing us with our first visual glimpse of this potential diamond world. In many ways, 55 Cancri E embodies the wonder and mystery of exoplanet exploration. It's a world that defies our expectations, challenging us to expand our understanding of what's possible in the universe. Whether it turns out to be a diamond planet, a lava world, or something else entirely, 55 Cancri E reminds us that the cosmos is full of wonders beyond our imagination. As we leave this glittering, scorching world behind, we carry with us a renewed sense of awe at the diversity of planets in our galaxy. From infernal furnaces to diamond downpours, each world we encounter expands our cosmic perspective. And as we journey on to our next destination, we're left to wonder, what other impossible worlds await our discovery in the vast expanse of the universe? The Windwalker, HD 189733b. From the diamond rains of 55 Cancri E, we now venture to a world where the very concept of weather takes on a whole new meaning. Welcome to HD 189733b, a planet where winds howl at supersonic speeds and glass rains sideways through the air. This is a world that redefines our understanding of atmospheric dynamics and challenges our notions of what a planetary environment can be. Located approximately 63 light-years away in the constellation Vulpecula, HD 189733b orbits a K-type orange dwarf star. This planet falls into the category of hot Jupiters, gas giants that orbit extremely close to their parent stars. But even among hot Jupiters, HD 189733b stands out for its extreme conditions and the wealth of information we've been able to gather about it. One of the first things you'd notice about HD 189733b, if you could somehow view it from space, is its color. Unlike the oranges and browns of our own gas giants, HD 189733b appears a deep, striking blue. This isn't the blue of Earth's oceans, however. The color comes from light scattering through a hazy, turbulent atmosphere laden with silicate particles. In other words, from light bouncing off microscopic shards of glass. But the color is just the beginning of what makes HD 189733b extraordinary. This planet is a world of weather extremes that make Earth's most violent storms look like gentle breezes in comparison. Let's start with the wind. On HD 189733b, wind speeds have been measured at up to 5,400 miles per hour, or 8,700 kilometers per hour. For context, that's about 7 times the speed of sound on Earth. These winds aren't just fast, they're hypersonic. Imagine for a moment what it would be like to experience such winds. They would be powerful enough to pick up and accelerate objects to bullet-like speeds. The roar would be deafening, if sound could even propagate normally in such conditions. And the force would be strong enough to flatten any structures and rip apart anything not anchored extremely securely. But the extreme winds are just one aspect of HD 189733b's terrifying weather. Remember those silicate particles that give the planet its blue color? In the upper atmosphere, where temperatures are somewhat cooler, these particles can condense into droplets, forming clouds. But these aren't the fluffy white clouds we're used to on Earth. These are clouds of molten glass. As these glass droplets fall through the lower, hotter parts of the atmosphere, they heat up and vaporize again, creating a cycle of glass rain that never actually reaches the surface. And given the extreme winds, this rain doesn't fall straight down. Instead, it's whipped sideways, creating what is essentially a never-ending storm of hot glass shards hurtling through the air at thousands of miles per hour. The temperature on HD 189733b is another factor that sets it apart. Like many hot Jupiters, this planet is tidally locked to its star, meaning the same side always faces the star. This creates an extreme temperature difference between the day and night sides of the planet. The dayside temperature of HD 189733b is estimated to be around 1,000 degrees Celsius, or 1,832 degrees Fahrenheit, hot enough to melt lead. The night side, while cooler, is still incredibly hot by Earth standards. This temperature differential drives the planet's extreme weather. Hot air from the day side rises and moves towards the cooler night side, while cooler air from the night side sinks and moves towards the day side. This creates a global wind pattern that, combined with the planet's rotation, results in the hypersonic winds we observe. The study of HD 189733b has been a triumph of modern astronomy and has pushed the boundaries of what we can learn about distant worlds. When it was first discovered in 2005, we could only measure its basic properties, its mass, radius, and orbit. But over the years, thanks to advances in technology and observational techniques, we've been able to probe deeper into this planet's nature. One of the most significant breakthroughs came in 2007, when astronomers used the Spitzer Space Telescope to create the first ever weather map of an exoplanet. By observing how the infrared light from the planet changed as it orbited its star, they were able to create a crude temperature map of HD 189733b's surface. This map confirmed the extreme temperature difference between the day and night sides and provided evidence for winds redistributing heat around the planet. Further studies have allowed us to probe the composition of HD 189733b's atmosphere. Using a technique called transit spectroscopy, where we analyze how the star's light changes as it passes through the planet's atmosphere during a transit, astronomers have detected the presence of water vapor, carbon monoxide, and possibly methane in the planet's air. They've even detected evidence of escaping hydrogen, suggesting that the planet's atmosphere is slowly being stripped away by its star's intense radiation. The blue color of HD 189733b wasn't confirmed until 2013, when observations from the Hubble Space Telescope allowed astronomers to measure the planet's color directly. This was the first time the color of a planet outside our solar system had been determined. The deep blue hue came as a surprise to many, as it's quite different from the colors of the gas giants in our own solar system. One of the most intriguing aspects of HD 189733b is how it challenges our models of planetary formation and evolution. According to traditional models, gas giants should form far from their parent stars, where temperatures are cool enough for gases to condense and for the planet to accumulate mass. So how did HD 189733b end up so close to its star? The leading theory is that the planet formed further out in its solar system and then migrated inward. This process, known as planetary migration, is thought to be common in the early stages of solar system formation, but the exact mechanisms of this migration and why it results in some planets stopping so close to their stars while others remain further out are still subjects of ongoing research. The extreme conditions on HD 189733b also raise intriguing questions about the internal structure of hot Jupiters. The intense heat from the nearby star causes the planet's atmosphere to puff up, making it larger than it would be if it were orbiting further out. But this heat also affects the planet's interior in ways we're still trying to understand. Some models suggest that the intense stellar radiation could create a layer of electrically conducting hydrogen in the planet's outer layers, which could, in turn, generate powerful magnetic fields. These magnetic fields could interact with the charged particles streaming from the star, potentially creating auroras far more intense than anything we see on Earth. While we can't directly observe these auroras, they could potentially be detectable with future telescopes, providing another way to probe the nature of these extreme worlds. The study of HD 189733b and other hot Jupiters has implications that go far beyond these planets themselves. By understanding how these worlds form, migrate, and evolve, we gain insights into the processes that shape all planetary systems, including our own. The extreme conditions on these planets also allow us to test our models of atmospheric physics, climate dynamics, and even basic chemistry in regimes far beyond what we can replicate in Earth-based laboratories. Moreover, while HD 189733b itself is clearly inhospitable to life as we know it, studying its atmosphere and dynamics helps us refine our techniques for analyzing the atmospheres of smaller, potentially habitable worlds. The methods developed to detect water vapor and other molecules in HD 189733b's atmosphere are the same ones we hope to use one day to search for signs of life on distant Earth-like planets. As our technology continues to advance, we can look forward to learning even more about HD 189733b and planets like it. Future space telescopes may be able to create more detailed maps of the planet's surface temperature and wind patterns. We might be able to detect and track the massive storms that likely rage in its atmosphere, and we may even be able to probe deeper into its internal structure, helping us understand how these planets managed to survive so close to their stars. HD 189733b stands as a testament to the incredible diversity of worlds that exist in our galaxy. It reminds us that the universe is often more extreme and more bizarre than we can imagine. From its deep blue color to its glass rain and hypersonic winds, this planet embodies the wonder and terror of the cosmic frontiers we are just beginning to explore. As we leave this wind-whipped, glass-strewn world behind, we carry with us a new appreciation for the sheer variety of planetary environments that exist in the cosmos. In the howling storms of HD 189733b, we see a mirror of our own world's weather taken to unimaginable extremes. And as we journey on to our next cosmic destination, we're left to wonder, what other weather phenomena, what other blues, might be waiting for us in the vast expanse of the universe? The Rogue Wanderer, CFBDSIR 2149-0403. From the tempestuous skies of HD 189733b, we now venture into the cold, dark expanses between the stars. Our next destination is not a world orbiting a distant sun, but a lonely wanderer drifting through the cosmic void. Welcome to CFBDSIR 2149-0403, a rogue planet that challenges our understanding of what it means to be a world. Our next destination is not a world orbiting a distant sun, but a lonely wanderer drifting through the cosmic void. Welcome to CFBDSIR 2149-0403, a rogue planet that challenges our understanding of what it means to be a world. Discovered in 2012, CFBDSIR 2149, 0403 is what astronomers call a rogue or free-floating planet. Unlike the worlds we've explored so far, this planet is not bound to any star. Instead, it drifts freely through space, untethered and alone. This solitary journey makes CFBDSIR 2149, 04003 one of the most mysterious and intriguing objects in our galaxy. The very existence of rogue planets like CFBDSIR 2149, 0403 forces us to reconsider our definitions of what constitutes a planet. Traditionally, we've thought of planets as bodies that orbit stars, but rogue planets show us that a world can exist independently, raising profound questions about planetary formation and the dynamics of galactic evolution. CFBDSIR 2149, 0403 was first spotted by the Canada-France-Hawaii telescope, and its discovery was later confirmed using the Very Large Telescope in Chile. It's located approximately 100 light-years from Earth, in a region of space associated with a group of young stars called the AB Doradus Moving Group. This association has led astronomers to estimate that CFBDSIR 2149, 0403 is relatively young in cosmic terms, perhaps only 50 to 120 million years old. But what exactly is CFBDSIR 2149, 0403? Estimating its size and mass has been a challenge for astronomers. Initial observations suggested it was about 4 to 7 times the mass of Jupiter, placing it in a gray area between planets and brown dwarfs. Brown dwarfs are objects more massive than planets, but not massive enough to sustain hydrogen fusion in their cores, which is what powers stars. The uncertainty about CFBDSIR 2149, 0403's exact nature highlights one of the key challenges in studying rogue planets. Without a host star to provide context and a means of measurement, determining the basic properties of these objects becomes incredibly difficult. Astronomers have had to rely on the planet's faint glow and models of how giant planets and brown dwarfs cool over time to estimate its mass and age. One of the most fascinating aspects of CFBDSIR 2149, 0403 is its temperature. Despite not having a star to warm it, this rogue world is not as cold as you might expect. Its surface temperature is estimated to be around 400 degrees Celsius, or 750 degrees Fahrenheit. While this is far cooler than the scorching hot Jupiters we've explored, it's still hot enough to melt lead. This warmth is thought to come from the heat of formation trapped in the planet's interior. When a planet forms, it accumulates a tremendous amount of energy from the collisions of the material that comes together to create it. In the case of a rogue planet like CFBDSIR 2149, 0403 with no star to provide external heating, this residual heat of formation can take billions of years to radiate away completely. The atmosphere of CFBDSIR 2149, 0403 would be a complex and dynamic place. Without a star to drive weather patterns, any atmospheric movement would be driven solely by the planet's internal heat and rotation. This could lead to banded structures similar to those seen on Jupiter, or perhaps more complex patterns that we've never observed before. One of the most intriguing possibilities is that CFBDSIR 2149, 0403 might have moons. Many of the gas giants in our solar system have extensive moon systems, and there's no reason to think that rogue planets would be any different. These moons, if they exist, would be truly alien worlds, cold, dark, and far from any star, their only source of heat and light the faint infrared glow of their parent planet. The discovery of CFBDSIR 2149, 0403 and other rogue planets has profound implications for our understanding of planetary formation and galactic evolution. How do these lone worlds come to be? There are several theories, each with intriguing implications. One possibility is that rogue planets form in the same way as other planets, within the protoplanetary disk around a young star, but are then ejected from their solar systems through gravitational interactions. This could happen if the planet comes too close to another massive body, perhaps another planet or a passing star. The gravitational slingshot effect could provide enough energy to break the planet free from its star's gravitational pull, sending it hurtling into interstellar space. If this is indeed how most rogue planets form, it suggests that the early stages of solar system formation are far more chaotic and violent than we once thought. It would mean that for every planetary system that survives intact, there might be numerous planets flung out into the void. This has led some astronomers to speculate that there could be far more rogue planets in our galaxy than there are stars. Another possibility is that some rogue planets form directly from the collapse of small pockets of gas and dust in molecular clouds, in a process similar to star formation, but on a smaller scale. This theory is particularly intriguing because it blurs the line between planet formation and star formation, suggesting a continuum of object types from small planets all the way up to massive stars. The study of rogue planets like CFBDSIR 2149, 0403 also has implications for our search for life in the universe. While a sunless world drifting through the cold of space might seem an unlikely abode for life, some scientists have proposed scenarios where even rogue planets could potentially harbor life. One possibility is that a rogue planet with a thick hydrogen atmosphere could retain enough heat to maintain liquid water on its surface, even without the warmth of a star. The hydrogen would act as a greenhouse gas, trapping the planet's internal heat. While this is a highly speculative scenario, it opens up the possibility that life could exist in places we never expected to find it. Another intriguing possibility is that life could exist on moons orbiting a rogue gas giant. If the planet is massive enough and retains enough internal heat, it could potentially provide enough energy to maintain a subsurface ocean on an icy moon, similar to what we believe exists on moons like Europa and Enceladus in our own solar system. The discovery of CFBDSIR 2149-0403 and other rogue planets has also raised questions about the potential for interstellar travel. Some scientists have proposed that if humanity ever develops the technology for interstellar exploration, rogue planets could serve as stepping stones between the stars. These worlds could provide resources and a place to rest and refuel on long interstellar journeys. As our technology improves, we hope to learn more about CFBDSIR 2149-0403 and other rogue planets. Future telescopes may be able to directly image these objects, providing more accurate measurements of their size, mass, and composition. We may be able to detect weather patterns in their atmospheres, or even spot moons orbiting them. One particularly exciting prospect is the possibility of detecting rogue planets through gravitational microlensing. This technique, which uses the gravitational field of a foreground object to magnify the light of a background star, is particularly sensitive to detecting isolated objects, like rogue planets. Future space-based microlensing surveys could potentially discover thousands of rogue planets, giving us a much better understanding of how common these objects are and how they're distributed throughout our galaxy. The study of rogue planets like CFBDSIR 2149-0403 is still in its infancy, and each new discovery brings with it new questions and challenges. These lonely wanderers represent a new frontier in planetary science, pushing us to expand our definitions and rethink our models of how planets form and evolve. As we leave CFBDSIR 2149-0403 behind, drifting silently through the interstellar void, we're left with a profound sense of the vastness and diversity of our universe. In the cold, dark spaces between the stars, worlds beyond our imagination await discovery. These rogue planets, lonely but unbound, remind us that the cosmos is full of wonders we're only beginning to understand. Our journey through the scariest planets in the cosmos has taken us from scorching hot Jupiters to diamond worlds, from glass storms to lonely wanderers. Each of these extreme environments pushes the boundaries of what we thought possible, challenging our understanding of physics, chemistry, and planetary science. As we continue our exploration of the universe, we can be certain that more surprises await us, more worlds that will astound and terrify us with their alien beauty and unimaginable conditions. In the story of CFBDSIR 2149-0403, we see a reflection of our own planet's journey through the cosmos. Earth, too, is in many ways a rogue planet, not tethered to any particular spot in the galaxy, but instead orbiting a star that itself orbits the galactic center. As we contemplate the vast cold journey of this rogue world, we're reminded of our own cosmic voyage and the incredible coincidences of physics and chemistry that have made our world not just habitable, but thriving with life. As we prepare to venture on to our next cosmic destination, we carry with us the image of CFBDSIR 2149-0403, a world alone in the vastness of space, silently testifying to the incredible diversity of planets that populate our galaxy. What other worlds, what other stories await us in the cosmic ocean? Only time and our continued exploration will tell. The Hellish twin, Venus. From the cold, dark expanse of interstellar space, we now turn our gaze closer to home. Our next destination is a world that has captured human imagination for millennia, a planet that shines brightly in our night sky and has been called Earth's twin. But don't be fooled by its beauty or its nickname. Welcome to Venus, a world so hostile it makes the term hellscape seem like an understatement. From the cold, dark expanse of interstellar space, we now turn our gaze closer to home. Our next destination is a world that has captured human imagination for millennia, a planet that shines brightly in our night sky and has been called Earth's twin. But don't be fooled by its beauty or its nickname. Welcome to Venus, a world so hostile it makes the term hellscape seem like an understatement. Venus, the second planet from the Sun, is often called Earth's evil twin, and for good reason. At first glance, Venus and Earth seem remarkably similar. They're close in size, mass, and composition, and they formed in the same region of the solar system at roughly the same time. But that's where the similarities end. Venus has evolved into a world so extreme, so utterly inhospitable, that it serves as a stark warning of how a planet similar to Earth can go terribly wrong. Let's start with the basics. Venus is a terrestrial planet like Earth, with a solid rocky surface. It's only slightly smaller than Earth, with about 80% of Earth's mass. Its day is longer than its year. Venus takes 243 Earth days to rotate once on its axis, but only 225 Earth days to orbit the Sun. And unlike most planets in our solar system, Venus rotates retrograde, meaning it spins in the opposite direction to its orbit. But it's when we look at Venus's surface and atmosphere that things get truly frightening. The surface of Venus is the hottest of any planet in our solar system, with an average temperature of about 462 degrees Celsius, or 864 degrees Fahrenheit. That's hot enough to melt lead, zinc, and several other metals. And unlike the gas giants we've explored, where the heat dissipates as you move away from the core, on Venus, this scorching temperature is at the surface. The cause of this extreme heat is Venus's runaway greenhouse effect. The planet's atmosphere is incredibly thick. The surface pressure on Venus is about 90 times that of Earth at sea level. It's like being 900 meters or 3,000 feet deep in Earth's oceans. This atmosphere is composed almost entirely of carbon dioxide, with small amounts of nitrogen and traces of other gases. The thick CO2 atmosphere traps heat incredibly effectively. Sunlight can penetrate the atmosphere and heat the surface, but the resulting infrared radiation can't escape back into space. This leads to a continual heating cycle that has turned Venus into a planetary oven. But the heat isn't the only thing that makes Venus's atmosphere terrifying. High in the atmosphere, there's a thick layer of clouds made primarily of sulfuric acid. These clouds are so reflective that they're the reason Venus appears so bright in our night sky. But they're also incredibly corrosive. Any spacecraft or probe we send to Venus has to be specially designed to withstand this acid bath, at least for a short while. Below the acid clouds, as we descend towards the surface, things get even more extreme. The atmospheric pressure increases dramatically. At the surface, the CO2 is in a supercritical state, neither truly a gas nor a liquid, but with properties of both. It's so dense that it behaves almost like an ocean. In fact, if you could somehow survive the heat and pressure, you might be able to swim through the lower atmosphere of Venus. The surface of Venus itself is a barren, rocky landscape, baked by the intense heat and crushed under the enormous atmospheric pressure. The entire planet is covered in volcanic features, vast plains of basaltic lava, enormous shield volcanoes, and strange corona formations that are thought to be the result of upwellings of magma. One of the most intriguing features of Venus's surface is its tesserae, highly deformed regions that make up about 8% of the planet's surface. These regions are higher than the surrounding plains and are intensely fractured and folded. Some scientists think these might be the oldest terrains on Venus, possibly remnants of a time when the planet was very different. Venus also has several large impact craters, but far fewer than we see on other rocky bodies like the Moon or Mars. This is because Venus's thick atmosphere burns up most smaller meteors before they can reach the surface. The craters we do see are all relatively fresh. Venus's surface appears to have been completely resurfaced by volcanic activity within the last billion years or so. The history of Venus, and how it came to be so different from Earth, is a subject of intense scientific interest. Both planets likely started out very similar, possibly even with oceans of liquid water on their surfaces. But at some point, Venus took a different path, entering a runaway greenhouse state that eventually led to its current hellish conditions. One theory suggests that as the young sun grew brighter, it heated Venus's oceans, causing water vapor, a potent greenhouse gas, to build up in the atmosphere. This led to more heating, which vaporized more water, creating a vicious cycle. Eventually, all the water was in the atmosphere, where it was broken apart by ultraviolet radiation. The hydrogen escaped into space, while the oxygen likely combined with elements in the crust. The result was a dry planet with a thick CO2 atmosphere, the Venus we see today. Another theory proposes that Venus's lack of a magnetic field played a crucial role. Without a magnetic field to protect it, Venus's atmosphere was steadily eroded by the solar wind. This could have stripped away lighter elements like hydrogen, leaving behind the heavy CO2 atmosphere. Venus's current state raises profound questions about planetary evolution and the concept of habitable zones around stars. It serves as a stark reminder of how delicate the balance is that keeps Earth habitable. Understanding Venus is crucial not just for unraveling the history of our solar system, but also for assessing the potential habitability of Earth-sized exoplanets we're discovering around other stars. Despite its hostile conditions, Venus continues to be a target for scientific exploration. Several spacecraft have visited Venus, including orbiters, atmospheric probes, and even a few short-lived landers. The Soviet Venera missions in the 1970s and 80s provided our only direct images of Venus's surface, showing a dim, rocky landscape under an orange sky. Future missions to Venus face incredible challenges. The extreme heat and pressure on the surface mean that even the most robust landers can only survive for a few hours at most. The thick atmosphere makes landing precisely difficult, and the acid clouds corrode spacecraft components. Yet the scientific value of exploring Venus is so high that space agencies around the world continue to develop new missions and technologies to study this enigmatic world. One of the most exciting areas of Venus research in recent years has been the possibility of life in the planet's atmosphere. While the surface of Venus is clearly inhospitable, the upper atmosphere, about 50 to 60 kilometers above the surface, has much more Earth-like conditions. At this altitude, the temperature and pressure are similar to those at Earth's surface. This has led some scientists to speculate that microbial life could potentially survive in Venus's upper atmosphere. This hypothesis gained significant attention in 2020 when a team of researchers announced the detection of phosphine in Venus's atmosphere. On Earth, phosphine is produced by industrial processes and by microbial life in oxygen-poor environments. Its presence on Venus, if confirmed, could be a potential biosignature. However, subsequent studies have questioned this detection, and the topic remains a subject of ongoing debate and research. Even if life isn't present on Venus now, studying the planet can tell us a lot about the potential for life on other worlds. Venus represents an endpoint of planetary evolution, a runaway greenhouse state that may be common for planets orbiting in the inner regions of their star's habitable zones. These questions have led to proposals for new types of Venus missions. Some scientists have suggested high-altitude balloons or solar-powered airplanes that could float in the more temperate regions of Venus's atmosphere, conducting long-term studies without having to contend with the hellish surface conditions. Others have proposed missions to study Venus's tesserae regions, which might preserve evidence of the planet's earlier, potentially more habitable period. There's also growing interest in the possibility of using Venus for a gravitational assist maneuver for missions heading to the outer solar system. As we continue to explore our cosmic neighborhood, Venus may serve as a vital waypoint, its gravity helping to fling spacecraft towards more distant targets. Venus also serves as a natural laboratory for studying climate change on a planetary scale. The runaway greenhouse effect that turned Venus into the world we see today is an extreme version of the greenhouse effect we're grappling with on Earth. By studying Venus, we can better understand the complexities of atmospheric physics and chemistry, potentially providing insights that could be crucial for managing Earth's changing climate. One of the most intriguing questions about Venus is whether it was ever truly Earth-like in the past. Some models suggest that Venus might have had liquid water oceans for billions of years, possibly right up until about 700 million years ago. If this is true, could life have evolved on Venus during this time? And if so, could any traces of that life still exist, perhaps in some protected niche? Venus challenges us to push the boundaries of our technology, to develop new ways of exploring hostile environments. It forces us to grapple with questions about planetary evolution, the nature of habitability, and the fragility of environments conducive to life as we know it. As we contemplate Venus, we're faced with a world that is at once familiar and utterly alien. Its size and composition mirror our own planet, yet its conditions are unimaginably hostile. In Venus, we see a possible future for Earth if runaway climate change were to occur. We see the importance of the delicate balance that keeps our own world habitable. And we're reminded of the incredible diversity of planetary environments that exist even within our own solar system. As we leave this hellish twin of Earth behind, we carry with us a new appreciation for the complexities of planetary science. In the searing heat and crushing pressure of Venus, we find a mirror that reflects back at us the preciousness of our own world. And as we journey on to our next cosmic destination, we're left to ponder. What other secrets might Venus be hiding beneath its impenetrable veil of clouds and acid rain? What lessons does this world of extremes still have to teach us about our own planet, our solar system, and the countless worlds beyond? The Dark Giant. Tres 2b. From the searing inferno of Venus, we now journey back into the depths of space, to a world shrouded in almost impenetrable darkness. Our next destination is a planet so dark it seems to devour light itself. Welcome to Tres 2b, the darkest known exoplanet in the universe. Discovered in 2006 by the Transatlantic Exoplanet Survey, Tres 2b orbits the star GSC 03549, 02811 in the constellation Draco, approximately 750 light-years from Earth. This alien world has captured the imagination of astronomers and the public alike, not for its scorching heat or extreme pressure, but for its mind-boggling darkness. Tres 2b is a hot Jupiter, a gas giant planet orbiting extremely close to its parent star. It completes an orbit every 2.5 Earth days, far closer to its star than Mercury is to our Sun. With such a tight orbit, you might expect Tres 2b to be blindingly bright, reflecting the intense starlight that bathes its surface. But this is where Tres 2b defies expectations in a truly spectacular way. In 2011, measurements from NASA's Kepler Space Telescope revealed something astonishing. Tres 2b reflects less than 1% of the light that falls on it. To put this in perspective, even black acrylic paint reflects about 5% of light, and our moon reflects about 12%. Tres 2b is darker than any planet or moon we've ever discovered. Just how dark is Tres 2b? Imagine a black so deep that it's almost impossible to see. If you could somehow visit this alien world, you'd be enveloped in near total darkness. The planet would be barely visible, a faint reddish glow emanating from its heat, the only thing distinguishing it from the backdrop of space. It's a world of perpetual night, where even the concepts of day and shadow lose meaning. But what could make a planet so incredibly dark? The answer lies in the exotic composition of Tres 2b's atmosphere. Scientists believe that the planet's atmosphere contains light-absorbing chemicals like vaporized sodium and potassium, or perhaps compounds of titanium oxide. These substances, combined with the intense heat from the nearby star, create a light-trapping effect that results in the planet's extreme darkness. The heat on Tres 2b is truly extreme. With a surface temperature estimated at over 1,000 degrees Celsius, or about 1,800 degrees Fahrenheit, it's hot enough to melt aluminum. This intense heat plays a crucial role in the planet's darkness. At such high temperatures, molecules in the atmosphere that might normally reflect light break down, and new light-absorbing compounds can form. Despite its darkness, Tres 2b isn't completely invisible. The The same heat that contributes to its light-absorbing properties also causes the planet to glow faintly, like a hot ember. This glow, combined with slight variations in the planet's cloud cover, results in subtle changes in brightness as the planet orbits its star. It's these tiny fluctuations that allowed astronomers to measure TRES 2b's reflectivity in the first place. The study of TRES 2b has been a triumph of modern astronomical techniques. The planet is far too distant to be imaged directly with current technology. Instead, astronomers have had to rely on indirect methods to learn about this dark world. The primary method used to study TRES 2b is known as the transit method. As the planet passes in front of its star from our perspective, it blocks a tiny fraction of the star's light. By measuring this dip in brightness, astronomers can determine the planet's size. The transit method also allows us to study the planet's atmosphere. As starlight passes through the thin upper layers of the planet's atmosphere during a transit, certain wavelengths are absorbed by the gases present. By analyzing this absorption spectrum, scientists can determine the composition of the planet's atmosphere. Another technique used to study TRES 2b is known as phase curve analysis. As the planet orbits its star, we see different phases of the planet illuminated, similar to the phases of our moon. By carefully measuring the minute changes in the total light from the star system as the planet goes through these phases, astronomers can map the temperature distribution across the planet's surface and even detect the presence of clouds or hotspots. These observations have revealed that TRES 2b, like many hot Jupiters, is likely tidally locked to its star. This means that the same side of the planet always faces the star, resulting in a permanent day side and a permanent night side. This tidal locking creates extreme temperature differences between the two sides of the planet, driving powerful winds that distribute heat around the planet. The extreme conditions on TRES 2b raise intriguing questions about its internal structure and evolution. How does a planet maintain its gaseous envelope under such intense stellar radiation? How do the powerful winds and extreme temperature gradients affect the planet's internal dynamics? These are questions that push the boundaries of our understanding of planetary physics. One particularly interesting area of research is the study of TRES 2b's magnetic field. The intense heat from the nearby star causes the planet's atmosphere to become partially ionized, potentially generating powerful electrical currents. These currents could in turn create a strong magnetic field. This field might play a crucial role in protecting the planet's atmosphere from being stripped away by the stellar wind. The darkness of TRES 2b also has implications for the search for life in the universe. While TRES 2b itself is far too hot to be habitable, its discovery reminds us that planets can have a wide range of albedos or reflectivities. This is important because albedo is one of the factors that determine a planet's surface temperature and potential habitability. The existence of extremely dark planets like TRES 2b suggests that we need to consider a broader range of possibilities when assessing the potential habitability of exoplanets. Moreover, the techniques developed to study TRES 2b and other hot Jupiters are paving the way for the study of smaller, potentially habitable worlds. The ability to detect minute changes in a star's light and to analyze the faint spectral signatures of planetary atmospheres are crucial skills that will be applied to the search for biosignatures on distant Earth-like planets. The story of TRES 2b is also a story about the evolution of our observational capabilities. When it was first discovered in 2006, we knew little about this world beyond its basic orbital parameters. The revelation of its extreme darkness came 5 years later, thanks to the exquisite precision of the Kepler Space Telescope. As our technology continues to advance, we can look forward to learning even more about this and other exotic worlds. Future missions like the James Webb Space Telescope and the proposed LUVOIR, Large UV/Optical/IR Surveyor Telescope, promise to revolutionize our study of exoplanet atmospheres. These instruments may be able to create detailed chemical maps of TRES 2b's atmosphere, helping us understand the exact mix of compounds that make this world so dark. They might even be able to detect weather patterns or storms in the planet's atmosphere, giving us a more dynamic picture of this alien world. The existence of TRES 2b also sparks the imagination. What would it be like to visit such a world? While we'll likely never send a probe to TRES 2b itself, the planet serves as inspiration for scientists and engineers developing technologies for exploring extreme environments. The challenges of operating in intense heat and near total darkness are not unlike those faced by probes designed to explore the cloud layers of Venus or the hydrocarbon seas of Saturn's moon Titan. In popular culture, TRES 2b has captured the public imagination, appearing in science fiction stories and artworks. Its almost total darkness makes it the perfect setting for tales of the unknown and the mysterious. In this way, TRES 2b serves as a bridge between scientific discovery and human creativity, inspiring us to think about the vast possibilities that exist in the cosmos. As we contemplate TRES 2b, we're confronted with the sheer diversity of worlds that exist in our galaxy. From scorching hot planets to frigid ice worlds, from rocky Earth-like planets to gas giants, and now to a world darker than coal, the universe continues to surprise us with its inventiveness. Each of these worlds is a piece in the grand puzzle of planetary formation and evolution, helping us understand how our own solar system came to be, and what other arrangements might exist around distant stars. The darkness of TRES 2b also serves as a metaphor for our exploration of the cosmos. Just as this planet absorbs nearly all the light that falls on it, space itself often seems to swallow our efforts to understand it. Yet through patience, ingenuity, and the persistent application of scientific methods, we continue to shine light into the darkness, revealing the secrets of these distant worlds. As we leave TRES 2b behind, its inky blackness fading into the cosmic night, we carry with us a renewed sense of wonder at the universe's capacity to surprise us. In the depths of space, in the darkest of worlds, we find not emptiness, but new frontiers of knowledge waiting to be explored. And as we journey on to our next destination, we're left to wonder, what other dark secrets, what other mind-bending revelations await us in the vast expanse of the cosmos? In the enigma of TRES 2b, we see reflected our own unquenchable curiosity, our drive to push back the boundaries of the unknown, to bring light to even the darkest corners of the universe. The impossible world. J1407b. From the light-devouring darkness of TRES 2b, we now journey to a world that challenges our very understanding of what a planet can be. Welcome to J1407b, a planet so extraordinary that it has been dubbed Super Saturn and the Lord of the Rings. This is a world that pushes the boundaries of what we thought was possible in planetary formation and structure. Discovered in 2012 by a team led by Eric Mamajek, J1407b orbits a young star known as J1407, full designation 1, SWASP J140747.93, 394,542.6, located about 434 light-years away in the constellation Centaurus. But it's not the planet itself that makes J1407b so remarkable. It's the planet's ring system, which is so vast and complex that it defies imagination. To understand just how extraordinary J1407b's rings are, let's start with a comparison to our own solar system's ringed wonder, Saturn. Saturn's rings, while impressive, extend to about 175,000 kilometers from the planet's surface. Now, consider this. The ring system of J1407b is estimated to extend up to 90 million kilometers from the planet. That's about 200 times larger than Saturn's rings. If we were to replace Saturn's rings with those of J1407b, they would dominate our night sky, appearing many times larger than the full moon. The outer edges of the ring system would extend nearly halfway to Earth. It's a structure so vast that it almost defies classification as a planetary feature. It's more like a miniature solar system in its own right. But size isn't the only thing that makes J1407b's ring special. Observations suggest that the ring system is incredibly complex, with over 30 distinct rings identified so far. These rings aren't uniform, they vary greatly in density and size, with some areas of the rings much thicker than others. There's even evidence of gaps in the rings, possibly carved out by moons orbiting within the ring system itself. The discovery of J1407b and its extraordinary rings was made possible by a phenomenon known as an occultation. As the planet and its rings passed in front of its parent star, they blocked out the star's light in a complex pattern. By carefully analyzing this pattern, astronomers were able to reconstruct the structure of the ring system with remarkable detail. What's particularly fascinating about this occultation is its duration. The star's light was affected by the rings for a period of 56 days, further emphasizing the sheer scale of this structure. It's like a solar eclipse lasting for nearly 2 months. But what could create such an enormous and complex ring system? The leading theory is that we're observing J1407b at a very specific and rare point in its history. The planet and its ring system are thought to be quite young, perhaps only about 16 million years old. This could represent an early stage in the formation of a moon system. In this scenario, the rings of J1407b are made up of debris left over from the planet's formation. Over time, this material would normally coalesce into moons. Indeed, the gaps observed in the ring structure might indicate that this process is already underway, with larger bodies or proto-moons carving out spaces in the rings. If this theory is correct, then J1407b provides us with a unique opportunity to observe a process that likely occurred in our own solar system billions of years ago. It's like looking back in time to see how the moons of Jupiter or Saturn might have formed. The composition of J1407b's rings is another area of intense scientific interest. While we can't directly sample the material, spectroscopic observations and models based on the ring's interaction with starlight provide some clues. The rings are likely composed primarily of dust and ice particles, similar to Saturn's rings but on a much grander scale. Some scientists have even speculated about the possibility of rocky material in the rings, particularly in the denser regions. Could some of these ring particles be large enough to be considered asteroids or planetesimals? The answer to this question could provide valuable insights into the process of planet and moon formation. As for J1407b itself, many questions remain. The planet's exact size and mass are still subjects of debate, as it's challenging to distinguish the planet from its enormous ring system in our observations. Current estimates suggest that J1407b is likely several times more massive than Jupiter, possibly in the range of 10 to 40 Jupiter masses. This uncertainty in J1407b's mass raises an intriguing possibility. Could J1407b be not a planet at all, but a brown dwarf, an object intermediate between a planet and a star? If so, it would be the first brown dwarf discovered with a ring system, further expanding our understanding of these enigmatic objects. The orbit of J1407b is another puzzle. Based on the duration of the occultation event, astronomers estimate that the planet likely has a very long orbital period, perhaps taking 11 or 12 years to circle its star. This places it much further from its star than Saturn is from our Sun, challenging our models of how such a massive ring system could remain stable at that distance. Moreover, the orbit of J1407b appears to be highly elliptical. This eccentric orbit could subject the ring system to varying gravitational forces as the planet moves closer to and further from its star, potentially causing dramatic changes in the ring structure over time. The study of J1407b and its rings has implications that go far beyond this single extraordinary system. It forces us to reconsider our models of planetary formation and evolution. How common are such massive ring systems in the galaxy? Are they a normal phase in the evolution of gas giant planets? Or is J1407b a rare exception? These questions tie into broader debates about the diversity of planetary systems in the universe. As we discover more exoplanets, we're continually surprised by the variety of worlds out there. J1407b stands as a testament to the fact that the universe is often more imaginative than we are in creating strange and wondrous worlds. The existence of J1407b also has practical implications for our search for exoplanets. The planet's massive ring system was key to its discovery. The complex pattern of the stars dimming during the occultation event was what caught astronomers' attention. This suggests that looking for similar occultation patterns could be a valuable method for detecting other ringed planets or complex planetary systems. Moreover, the study of J1407b's rings could provide insights into the dynamics of debris disks around young stars. These disks, composed of dust and gas, are the birthplaces of planets. By understanding how material in J1407b's rings interacts and potentially coalesces into larger bodies, we might gain a better understanding of the early stages of planet formation. The future study of J1407b promises to be exciting. As our observational technologies improve, we may be able to create more detailed maps of the ring system, possibly even detecting the forming moons within the gaps. The James Webb Space Telescope, with its unprecedented sensitivity and resolution, could provide new insights into the composition of the rings and the nature of J1407b itself. There's also the tantalizing possibility of watching the evolution of this system in real time. If J1407b's rings are indeed a transient feature, representing an early stage of moon formation, then over the coming decades, we might be able to observe changes in the ring structure. This would provide a unique opportunity to watch planetary evolution in action, testing our theories about how moons form and how ring systems evolve. The discovery and study of J1407b also sparked the imagination in other ways. What would it be like to visit such a world? Imagine standing on a moon within J1407b's ring system. The sky would be dominated by the vast expanse of the rings, a celestial bridge stretching from horizon to horizon. Depending on your location within the system, you might see a constant stream of ring particles overhead, or find yourself in the shadow of a particularly dense ring section. The rings would likely create spectacular visual effects. Sunlight filtering through the rings could create complex patterns of light and shadow on any moons or on the planet itself. The interactions between the planet, its moons, and the ring particles could lead to constant dynamic changes in the sky, a celestial dance on a scale that dwarfs anything in our solar system. From a more practical standpoint, the existence of a system like J1407b raises interesting questions about the potential for life and the challenges of space exploration in such an environment. While J1407b itself is likely inhospitable to life as we know it, could moons within its ring system potentially harbor life? How would the constant influx of ring material affect the development of a biosphere? And how would a civilization arising in such a system develop space travel when faced with the navigational hazards posed by the dense ring system? As we contemplate J1407b, we're once again reminded of the incredible diversity of worlds that exist in our galaxy. From scorching hot planets to frigid ice worlds, from planets darker than coal to worlds encircled by impossibly vast ring systems, the universe continues to surprise us with its creativity. J1407b stands as a cosmic exclamation point, a world that forces us to expand our definitions and rethink our assumptions about what's possible in planetary science. It's a reminder that even as we make new discoveries, the universe always has more secrets to reveal, more wonders to unveil. As we leave this ring-encircled giant behind, its vast celestial bridges fading into the cosmic distance, we carry with us a renewed sense of awe at the sheer scale and variety of structures that can exist in space. In the impossibly vast rings of J1407b, we see reflected our own unquenchable curiosity, our drive to understand the most extreme and unusual phenomena in the cosmos. And as we journey on to our final destination in this tour of the universe's scariest planets, we're left to wonder, what other impossible worlds, what other mind-bending celestial structures await our discovery in the vast, largely unexplored expanses of the cosmos? In J1407b, we see not just a single extraordinary world, but a promise of countless other marvels waiting to be revealed by our ever-improving tools and our relentless quest for knowledge. In our journey through the cosmos, we've witnessed worlds that defy imagination, planets where diamonds rain from the sky, where winds howl at hypersonic speeds, and where darkness reigns supreme. Each of these alien worlds has shown us that the universe is far stranger and more terrifying than we ever dared to dream. But for every world we've explored, countless others await discovery. Our galaxy alone hosts hundreds of billions of stars, many of which likely harbor their own families of planets. And beyond our galaxy, there are trillions more galaxies, each an island universe unto itself, each home to its own collection of cosmic terrors and wonders. As we push the boundaries of our knowledge and our technology, we draw ever closer to answering some of humanity's most profound questions. How did we get here? Are we alone in the universe? What is our place in this vast cosmic ocean? Every scary planet we study, every extreme world we discover, brings us one step closer to understanding our own cosmic home. In the hellish heat of Kelt 9b, we see the forces that Earth has kept in check for billions of years. In the crushing pressure of Venus, we're reminded of the delicate balance that makes our world habitable. And in the lonely wanderings of rogue planets, we recognize the precious cosmic cradle that is our solar system. As we stand on the precipice of a new era of discovery, we're filled with a profound sense of humility and an equally profound sense of possibility. The universe has shown us that it's far more creative and diverse than we ever imagined. What other wonders await our discovery? What other terrors lurk in the cosmic depths? The same human ingenuity that allowed us to discover and study these extreme worlds is now pushing us forward into a new frontier of exploration. With each technological advance, with each new mission, we extend our cosmic reach, probing deeper into the unknown. The scary planets we've explored are more than just distant worlds. They are a challenge, a call to adventure that resonates with the explorer in each of us. They remind us that the universe is vast and largely unknown, filled with dangers, yes, but also with the potential for discovery and wonder beyond our wildest dreams. As we conclude our journey, we invite you to step outside tonight. Look up at the stars and remember, each point of light could be home to worlds as extreme and as fascinating as those we've explored. The next great discovery could be hiding in plain sight, waiting for curious minds and brave hearts to unveil its secrets. Our voyage through the scariest planets in the cosmos is not an end, but a beginning. It's an invitation to wonder, to explore, to push the boundaries of our knowledge and our imagination. For in our quest to understand these alien worlds, we ultimately come to better understand ourselves, our own world, and our place in this vast, terrifying, and beautiful universe. So the next time you look up at the night sky, remember the cosmos is calling. How will you answer?